Hello and welcome to this lecture on project scheduling. This is part 2. We are continuing the project scheduling items that we discussed about last lecture. This chapter there are 4 main topics. Understanding lags in precedence relationships and types of lags that are there. Understanding Gantt charts. Crashing projects, trying to complete projects at an earlier time than they would normally complete, and understanding different types of network models, including particularly activity on activity network models. So let's look at these. First of all, lags. The idea of a lag is there's an intended delay from when one project either starts or finishes until the next project either starts or finishes. Now, the most common lags are finish to start. This would be in a linear situation where project A finishes, but the next step doesn't begin immediately. There is an intentional necessary lag from the time the first step completes to the second step completes. Perhaps some other contractor has to come in and do something. Perhaps the inspector has to come in and verify that the electrical's been wired correctly and has to get sign off from that. Perhaps you have to call to get, in construction, you have to call to get somebody to come and indicate where the wires are under the ground before you start digging, and so on. So the most common type of logical relationship for a lag is the finish to start in the linear model. But you can also have finish to finish lags where where the two items are related based on when they finish rather than when the first one finishes and the next one starts. And you can even do lags based on start times, but those are much less common. So the finish to start lag, this again is the most common type of sequence, and I've added some colors in the diagram down there to kind of help illustrate this lag. What you'll see is that those last two steps, in this case it's a design check and blueprinting, and we can see that the time between those, the design check takes 5 units, so it starts at 6 and ends at 11 for B. C, the blueprinting, takes 7 units. It starts at 15 and ends at 22. Now the question is, why does it start at 15? All right, it follows B, which finishes at 11, but there's a lag there. So the 11 plus the lag actually ends up adding time. Now that doesn't normally happen. If you look at A and B, the finish time of A is the start time for B. There's no added delay there. But when there's a lag, and again, there's times when lags are necessary, they end up affecting the times in our charts. Now I added blue colors there to kind of illustrate that on box B, activity B, the blue bars are showing the end of activity B, and the blue we're highlighting the beginning of activity C, the blueprinting stage. The arrow itself goes from an end of a box to the start of a box, the end of B, and then the arrow is pointing to the start of C. So this is a finish to start lag. Right? You can look at the lag arrow, in other words, and you can, as you look at the lag arrow itself, you can see where's the lag arrow starting at, and it's starting at the end of a box. So it is a finish lag, and it's finished to, the arrow is pointing to the start of another box. And again, that's the most common, and that's because there's some intentional delay from when the project finishes until you can continue somewhere. If you're pouring concrete, there's obviously at least a 24-hour lag, if not a 48-hour lag, before you can do any work on that concrete. You want it to harden, and so on. That lag of 4 is not slack. We were talking about slack last lecture. But this is required time. That time stays in this network whether you're moving forward or backward, and you can't pull it out. That is not optional time. If we had a parallel path going through here, we can say, oh, well, those 4 days are not required. They are required times in our projects. Here's a finish to finish lag. We can see the diagram, and again, if I were to, here's my lag arrow, and if I were to see that this lag arrow is starting at the finish of R, so it's a finish to something, and the lag arrow ends at the finish of T, so it's a finish to finish lag. In this situation, you're trying to it's like the end of a mini project. You want all the sub activities to complete at a fixed date so that the next activity, in this case the interior construction, can all begin when the plumbing and the HVAC and the wiring are all done. And again, just for example, perhaps the wiring has to be inspected by electrician standards to make sure it's up to par before you do any other work on that. The other two types of lags are so uncommon that I'm not going to really say much about those. Okay, so here's a sample question. What is the early start time for activity C? And I can see I've got A, B, C, and D are my 4 activities, and they've got start times and finish times and durations. But activity C, I don't know what the start time is for that. I can see that there is a start to start lag in this one because the arrow from the start of A to the start of C is going in there. But what is that time going to be? And notice on C, I know that it finishes at 30, and that makes sense because D begins when C finishes at 30. But I also don't know the length of C. I don't know if it's 1, 2, 3, 4, whatever it is. If I knew this value, if I knew that it finished at 30 and had a length of 5, for example, I know this was a 25. If it's 30 and had a length of 3, I know this would be 27. So to figure out the start time, I also have to blur out the length there to figure that out. Okay, so if we're looking at this, what I can see is that activity C is going to have to begin no earlier than activity B finishing. So activity A is going to have the opportunity to have some lag in there. So when I know that C finishes at 29, I know that the time for activity C is 1, and I know that the lag is from A to C because A starts at 20 and it has to the lag has to have it the start of the lagged activity C has to be the same, so lag of 9. Okay, second thing we're looking at in this 4-part lecture is Gantt charts. Now Gantt charts are a nice visual timeline of a project. So we have a time vision start to finish of our project, and it's very, very nice. These can be in the in terms of days. They can be some projects take multiple years, and you can have Gantt charts on them. Obviously, you'd revise it many, many times over the years. But if you're building some huge Boeing 747 new jet engine, if you're creating the football stadium they have in Dallas with the great big screen there, it cost $1.2 billion or whatever it was. It took many years to do, and they had a timeline. They had to revise it as they went, but they always kind of knew where they should be 3 months from now, 6 months from now, something roughly, and it gave them a chance to work on that. Sometimes you start falling behind schedule and you need to crash your schedule. That's what we're going to talk about next in our lecture. But before we get to crashing, let's again just remember the idea of this Gantt chart model. And what we see on this Gantt chart model is that activity A and activity B both happen to begin at the same time. A is shorter, B lasts longer, takes more time. I can see activity C is here, and it looks that the end of A is the beginning of C. So more than likely, A is a prerequisite for C to get completed. Likewise, D seems to start when B is done without any lag between B and C. So those things probably go on there, and there might be some other activities. There might be some opportunities for float in here, although we're not seeing the float itself. I can see that activity C might be able to, if nothing depends on it. Well, C, I can see F depends on C, and then nothing depends on F. So there's probably an opportunity to do some changes there. But anyways, regardless of this, I can take my data and plug it into a Gantt chart format. Once I have my dates, when they're supposed to start, when they're supposed to begin in my projects, I can come up with this. Their Gantt charts have the advantages. They're very easy to create. They're very easy to understand. It gives us a nice baseline for our network. They're easy to update and control. And these activities have resources associated with them, so it gives me a nice visual way of saying when does a resource being consumed or used required for the project, and when can a resource be reallocated temporarily or even completely reassigned to a new project. So looking at these Gantt charts again, here's a project about signing the contract, doing the questionnaire, the target audience, survey sample. So we saw this, I think, in last lecture as well. We've got our predecessors with those where B and C both depend on A being completed, and D depends on both B and C being completed, and estimated durations. I can plug that information into a spreadsheet, or even better, into Microsoft Project, which is a program that is specifically designed for helping with project management, and will do your Gantt charts much easier than it is to type it into Excel and tweak with Excel, including one of the things that the Microsoft Project does in an Excel Gantt chart. Hand-created Gantt chart doesn't take into account our weekends. And you can even see on the diagram below that Saturday and Sunday here are kind of grayed out, and they don't count in our days. So we've got 4 days here: Wednesday, Thursday, Friday. Saturday, Sunday don't count. Monday, so 1, 2, 3, and then skip the weekend. 4 is done for this. So Microsoft Project is the tool to use if you're doing some professional project management. And there's some other tools out there. Excel is a free and easy, if you have access to Excel or Google Docs or some spreadsheet program. You can create a Gantt-like chart with those tools, but if you're really going to do project management, it's worth investing in a tool like Project. And you do the same thing. You plug in the dates and it'll do the charting for you just like Excel did. You can also identify the resources associated with each project as you're going along, and we can see when John Smith is being used. So John Smith is being used as part of Project 1, and John Smith is being used as part of Project Activity 4, but there's a window here where the John Smith resource is not being used. And if that was a lawyer, if that was an engineer, he could be looking over legal briefs or looking over electrical drawings for the organization during this window between Tuesday of the 27th and into December of the following week. And it appears John Smith isn't doing anything, if this is the rest of our diagram, after December after Wednesday on the week of December 4th. And at that point, John Smith could be taken off of this project completely and reassigned to a completely different project for the project manager to help coordinate those resources. And again, I hate referring to people as resources. At one level, I understand that I'm a resource and you're a resource in a company's organization, but valuing people and their contributions is a key to being a good manager. So even as I say, John Smith is a resource, I cringe with the idea that we treat people as objects rather than as valuable contributors, and their creativity matters. So I just have to say that whenever I talk about resources as people. So I've got a project and I've got a deadline when it's going to be done, but there are times when you decide I need to get this project done more quickly. That is a need to crash your project. You're crashing the schedule or crunching the schedule. You're compressing it, accelerating the completion date would be another way of saying that. And there's 3 main ways of crashing the schedule. First of all is to get your existing resources to be more productive. And part of the way you get people to be more productive, as I was just saying, is don't talk of them as resources and treat them as resources. There's actually a way that you might be able to give, crack the whip less hard can result in better performance. As people work overtime, you'll get more done. You'll pay extra for that, but your productivity per unit of work actually can start going down for a while as you work people too hard, especially if you work people at a high rate involving a lot of adrenaline without time for rest and recuperation. You're going to end up hurting your project, not helping your project. You don't get done more quickly. But improving existing resource productivity, there's ways to do that, and good managers are finding that out. There's also ways of changing the existing resources, and that can involve firing an unproductive person, but more often it's involving improving the processes within the organization, such as the technologies used or whatever strategies or documentation you're having to follow. The reports on office space, I can't think of the name of it, but TPS reports on office space. Let's belay those for the next month, and let's focus on this project and improve our management of the project. But the most common way of crashing a project is to increase the resources. By far, that's the most common method for shortening the duration of a project, is to throw resources at it. More money, shorter time, right? Time and money. By throwing money at a project, you can reduce the time of a project. If you want a car that goes faster, pay more money, you get a faster car, right? If you increase cost, you're going to save time. Time is money. Is a very a statement that has a lot of truth to it. It certainly has truth when it comes to crashing projects. By throwing money at the project, you can save time in the project. So that's our biggest one here, is that increasing resource. That's really what we're typically going to be talking about. This diagram kind of shows the idea of what we're looking at. There's a formula up there that says, the crash cost minus the normal cost. So the money you're spending on extra cost to crash it versus the time you're saving. The normal time minus the crash time. There's some days in there, hopefully. You're spending money to save time. And that's going to give you a slope. The more you're spending for a little bit of time savings is going to have a higher slope steeper. And if you're not spending very much but you're saving a lot of time, you're spending $1 but you're saving 10 days, then you're going to have a very different slope. The diagram at the bottom, what we're seeing here, the main thing to realize what we're talking about here is we're talking about time across the bottom. So if I want to finish the project here, it's going to cost this amount. If I want to finish the project here under normal, it's going to cost this amount. It costs me less to finish on my normal time. If I want to finish earlier, going to the left on my timeline, like shorter time, then my cost is going to be higher on this cost axis. So the slope is probably going to be going down. That's what we'd expect it to be. Our goal is to pay, the least amount of money possible. However, there might be advantages to finishing early, and I'm willing to pay the extra cost to finish early, to get it to market, to meet a contractual obligation or whatever. Calculating crashing costs has to do with following that simple formula about the change in cost over the change in time. And you can read the project example here and understand what we're talking about. So we want to crash a project. The normal activity for X takes 5 weeks and 12,000. If we want to finish it faster, crash it, and be done in only 3 weeks, we can do that, but it's going to cost us $32,000. So what we can figure out from that is we can spend $20,000 more money. Instead of paying 12, we can pay 32. That's $20,000 more money, and we'll save 2 weeks of time. So $20,000 save 2 weeks of time. The crashing cost in this case is $10 per week. Anything that can be crashed, you can figure out the savings there. So here we've got, in this case, 8 activities. And there's the normal time and cost when we created the project and project was funded. That's what we were planning on. We were expecting to spend $22,450 to complete the project in whatever 5 plus 7 plus 3 plus 5 plus 9 plus 4 plus 6 plus 8 days is. That's how long it was going to take. That's how much it was going to cost. If we want to accelerate it and reduce the time, so 5 days becomes 3 days, 7 days becomes 6, 3 becomes 2, 5 becomes 5. There's really no saving there. 9 becomes 3, and so on. But it cost us extra to do that. There's it's going to be $1,500 to do activity A instead of $1,000. It's going to be $4,000 to do activity C instead of $2,500. So our total project cost goes up, but we save time. Now, as we plug those numbers in, we can do on an activity by activity basis, we can see what the crashing cost is per day. So activity A, for example, I save 2 days and it cost me $500, that's $250 per day. Activity B, I save 1 day, it cost me $300, that's $300 a day. Activity C, I save 1 day and it cost me $1,500, so it has a $1,500 crashing cost, and so on. Activity D, 5 days to 5 days, there's no way to crash that one, that's why it's blank. So when we know the activity crashing cost per day, we can actually go back and plot on a day-by-day basis. If this project is completed in 19 days, it will cost this amount. If it's completed in 20 days, it'll cost a little bit less, 21 days, even less, 22 days. And I can take those points and I can figure out what they're going to look like. So I'm going to show you that chart in just a second. But I do want to say one example here. Using the information in this table, determine the lowest cost minimum completion time. So we've got our normal time, our minimum time, our per day crash cost. And we also have predecessors, which we didn't have in that last diagram. If I just go through this and do the quick math on it, I can say 4 days at $50 a day, 3 days at $30 a day, and so on. I can see all my costs, and these are different numbers that we had before. There's only A through F, and different times and per day costs. But I can do that math, and I can look at it and say, I'm going to save 830 days. But here's the deal. When I factor in the predecessors and I go through and make my critical path for this project, I'll realize that some of my savings are not on the critical path. And it doesn't really make sense to crash something that has slack associated with it that's not on the critical path. So factoring in the critical path with these costs, it's not going to be the entire $830, but it's going to be only $720 that we can save because critical path matters. Now, a lot of times we do these discussions, we're just talking about critical path options. So going back to where I was a second ago, and I kind of jumped here. Let me go back and pull this slide back up. So here I've got my, I've made my point about critical path. So now I've got my 27 days and 19 days. And I've got my values there. I can see at 19 days it's 34,000, and 20 days it's 30,000, and at 21 days it's exactly almost 30,000. I'm below that, so my cost drops below 30,000 around the 21st day. I can plot each of those information, each of those items. So here I drop below 30,000 on that 21st day roughly. And my chart looks like my chart from before. And again, I'll just jump back to the chart I had from before, where as I move across, as I spend more time, I can spend less money building it. It costs a premium to do it early. And this chart is showing the same thing. If I want it done in 19 days, it's going to cost me something like this. Notice that the crash all and the crash A, E, and H have the same cost. That's because the items that aren't A, E, and H are not on the critical path. So even though I can crash them, it's not going to give me any time savings. So my goal would be to crash the critical path elements, crashing A first, crashing A and E, and then crashing A and E in 11. And I get choices here on the path. So if I need to get this done in 22 days, I know exactly what I need to do to meet that obligation. Why would I need to get it done in 22 days? Well, there are other factors involved. There are, of course, your direct costs involved that are associated with the production. There are penalties for missing deadlines, contractual deadlines. There are penalties for missing market deadlines and missing big sales opportunities. There are penalties having to do with factory and warehousing, any number of things. There are other costs associated with the project and project completion. So what you actually can end up doing is, as you factor in the other elements of your project and the cost associated with those other elements of your project, as you add all those together, you can end up with this total cost chart up here. So I see my direct costs are going down over time. My overhead is going up. So there's a penalty at day 50 if I'm not meeting things by those dates. I add all those values up and I can get this total cost at the top. What this would tell me is that if I factored in my penalties and my the costs associated with missing market opportunities or paying contractual bills for going overboard, my goal is simply to maximize money, which means reducing costs. So somewhere right around here, around 46, 45, 46, 47, that would be my target timeline. I would do enough crashing to get me this savings on this slope where my overall cost is going down, but I wouldn't keep crashing, because even though I'll get done sooner, the benefit based on avoiding penalties and overhead, it's not actually saving me money there. So if I have to for some reason finish it at 35, I can, but if my goal is just to improve costs, maximize minimize expenses, I'm going to probably shoot for 45, 46, or 47 as my target date. So quick considerations when it comes to crashing. Determine the fixed and the variable costs. Only focus on the critical path. Look for your trade-offs on time and cost. When you've reached your target completion date, then you don't need to crash anymore. You've hit the goal you want to have, and make sure that your crashing costs that they're worth it, that they're better than the penalties you'd be paying for not crashing. Okay, last point, the activity on node versus activity on error. We've been using activity on node, where each node, in this example B, C, D, E, and F in the top diagram, are represented by nodes, and the arrows just show you the flow between those. That's by far the more common, but there are still other techniques, other models out there, such as the activity on arrow model, the AOA network model, where the nodes are more like states that you're reaching, and then the activity that transitions from one state to another state is represented by the arrows. So B, the same activity, which might be doing the HVAC or sending out party reservations or whatever it is represented on the arrows in this case and not on the nodes. And there are some advantages and some disadvantages to arrow and arrow networks, or whatever network model that you're using. The idea behind the AOA is that activities are on the arrows, hence the name AOA. This has traditionally been used in construction projects. So in that market, in that domain, there are still a lot of people who use that, even though the Microsoft Project is kind of pushing people toward activity on network, and Microsoft Project has become more popular. The activity on network models become more popular. The event nodes, they're easy to identify, they're easy to flag. Forward and backward pass is very similar to as an AON, so what we already know about AON for forward backward passing makes sense here. Two activities may not begin and end at common nodes, and dummy activities may be required based on that previous statement that we can't have them begin and end on common nodes. We're going to talk about dummy activities here in just a second. One advantage of the AON, which is what we've been using, is that we don't ever have to have these dummy activities, but we'll see here in just a second how these dummy activities become necessary. So activity on arrow networks. So your nodes are an event label with a start time and an end time, but the activity is described on the arrow, not the node. So the activity name and the duration is shown on the arrow here. So looking at, again, a very familiar kind of a project, questionnaire, sample survey, developing the presentation. A is a predecessor for both B and C, and then B and C are both predecessors for activity D. So if we look at this and start trying to do this in an AOA approach, I would see that the activity A, which again is represented by an arrow, not a node, the activity A, I don't have the duration on here, but I could have the duration 5 written under here, but this just shows the activity A, which has a duration of 5. From 1, when we do A, and then we get to 2, and we could say, the time, we could put the times in there, we could add the 5 in there and know what those numbers are. We've left all the numbers off in terms of start and end times. We're just focusing on the arrows themselves in this diagram. But 2 is when A is finished, B and C can both begin because A is the predecessor. So this diagram shows how basically a burst is working here. Now when we look at the fact that activity D requires both B and C to be completed, to do this we have to use dummy activities, because I can't have 2 D arrows in here. I'm not allowed to have a D arrow coming out of node 3 and a D arrow coming out of node 4. There's only one D arrow, there's only one D activity, which in this case is the survey sample, and it has a 13 duration. But for me to get to that D arrow, I need to indicate that B and C have joined back up. So I'm adding this extra node, and I'm adding a dummy activity by these dashed lines. Now the dashed lines don't have any time associated with them, but they just allow us to do our flow the way we want to do our flow. That's one way of doing our dummy line, and this does require us to use an extra activity to join 3 and 4 to a node 5 and then get to 6. Another way of doing this is to add the dummy activity between 3 and 4. Say these things join back together, and then we're up to a single node, and D can come straight from that single node into, in this case, node 5. So we can do our dummy activities. We can add an extra node, or we can just join the 2 related predecessor nodes. So you can see those are 2 different ways of looking at the same addition of dashed arrow dummy nodes, so that the activity D, which happens after 2 predecessors, there's only one activity D arrow in our network. And again, we don't have to even deal with dummy arrows and dummy activities in the AON model that we've been using before. So real quick here, some controversies. Networks can get very complex because projects get very complex. It's better to plan twice and cut once. It's better to do these strategies, but realize that these models, they're not perfect. They give you best estimates, so you're making decisions, but be flexible with your schedules. Respect the people you work with above all. It's going to help you in the long term by far. Having a bad network doesn't help. I mean, because the networks are complex doesn't mean don't put good data into the network. Garbage in, garbage out, good in, good out. The best information you put into your network, the best it's going to help you as a tool to be successful. They can be used inappropriately. These aren't gospel. These aren't written in stone. These aren't anything more than a tool. Just because something's written in Microsoft Word doesn't mean it's perfect. It's only as good as the statement of the person that's writing it in Microsoft Word. I can write in Microsoft Word, the world's going to end with next Friday night at 5 p.m. Just because it says it in Microsoft Word doesn't mean it's going to happen. Just because it says it in a schedule doesn't mean it's going to happen. The quality of the input determines the quality of the usefulness of the tool. So don't use your networks inappropriately. Use them as a tool to then make wise decisions. You still have free will. The people you work with still have free will. Respect that and understand that. If you're working with subcontractors, you have to have a network that everybody can see to and buy into that, and understand that master network. That's very important. You wouldn't want to have people having their own extreme. Now you can potentially limit some of their vision at times if it's necessary for proprietary reasons, but by and large, it's better for everybody to understand how what they're doing impacts other people as well. So there's an advantage of having a master network there. And to have common approaches, common methods, common standards, be as common as possible, so that again everybody's speaking the same language. We don't talk over each other or miss key information because we were thinking differently. And also that last statement there, there's been some research that says there tends to be a positive bias, which means the estimates tend to be overly optimistic in terms of their duration estimates. So just realize that what that really means is they're wrong. It happens to be overly optimistic, but the point is that research says that these dates are not exactly what we think they're going to be. Okay, so there we go. Have a good day, and talk to you soon.